So this semester in Physics 7A, we learned a little bit about fluids, and in this video I'm going to talk about some of their applications in bioengineering, or more specifically in medicine. And I'm going to be focusing on Bernoullis equation and the equation of continuity. So Bernoullis equation says that the pressure of a fluid plus 1/2 times the density of the fluid times the velocity of the fluid squared plus the density of the fluid times the acceleration due to gravity times the height of the fluid is equal to some constant. And the equation of the continuity says that the density of a fluid times the area of the cross-section of the fluid times the velocity of a fluid, this is all an initial condition, is equal to the density, the final density of the fluid times the final area of the cross-section of that fluid times the final velocity of that fluid. All right, so what do these two mean exactly? So Bernoullis equation comes from Bernoullis principle that says where the velocity of a fluid is high, the pressure is low, and where the velocity is low, the pressure is high. And the equation of continuity pretty much says that the area of a cross-section of a fluid moving through something like a pipe, the lower the area, the higher the velocity for that same flow rate. So what that means exactly is much lower than at this point. So as a result, the velocity of the fluid at this point is going to be much higher than the velocity of the fluid at this point. So how does this relate to medicine? So in medicine, one of the many applications of Bernoullis principle is to explain TIA, which is a transient ischemic attack, which means a temporary lack of blood supply to the brain. A person suffering from TIA, they may experience symptoms such as dizziness, double vision, headache, and weakness of the brain. And so how do these occur? Well, a TIA, blood normally flows up the brain at the back of the head. This image is kind of like looking from behind someone, so this is the back of their head. So blood normally flows up the brain at the back of the head via the two vertebral arteries right here on either side of the head, which meet to form the basilar artery just below the brain, right up here. So the vertebral arteries issue from the subclavian arteries down here before they pass through the arms. So when the arm is exercised very vigorously, blood flow increases to meet the needs of the arm's muscles, right? So you're moving your arms a lot and you need to get oxygen to those muscles, so you have an increased flow rate to deliver that oxygen through the blood to those muscles. So if these subclavian arteries, so if the subclavian artery on one side of the body is partially blocked right here, we have a constriction here, such as like a blood clot, which can happen from arteriosclerosis, which is the hardening of artery, then the blood velocity at this point right here has to be much higher on this side to supply the needed blood, right? Looking back at the equation of continuity, we see that if that cross area is smaller, then we have to increase the velocity. Well, that's exactly what happens here. We have a much smaller area here relative to this bigger opening right here. So the velocity at this point of the blood will be much greater. So this increased blood velocity past the opening to the vertebral artery results in lower pressure, which, where did we see that? Bernoullis principle. That increase in velocity results in lower pressure. So the blood rising in the vertebral artery on the good side over here without the constriction at normal pressure can be diverted down into the other vertebral artery because of the low pressure on that side instead of passing upward to the brain. So it's not going up here, it's coming back down here. And that results in blood supply to the brain being cut off. And that's just one of many applications to fluids in medicine.